we will develop lower bounds for the variance of an unbiased estimator. So what does it mean? That if there is a lower bound for the variance of an unbiased estimator of a parametric function, then if I am able to develop an estimator and show that its variance is equal to the lower bound, then it becomes minimum variance unbiased estimator. Okay, so let me talk about this here. Equal to the lower bound. Then it becomes okay. So now let me talk about this, how these were developed. So these are all developed by several statisticians, and the prominent among them is Indian statistician C.R. Rao, 1945, Harold Kramer, 1947. But later on, because these are appearing in English language thing, but there are other things that were developed independently by some other statisticians also. So let me just mention the names of some of them. Fréchet in 1943, Darmoise in 1942. But these were not known. Actually, it became prominent only when C.R. Rao's paper in 1945 was published. And that is why the name is Rao-Kramer inequality in the statistical literature. So if you just Google Rao-Kramer inequality or Kramer-Rao inequality, you will find the details of this one. So in order to develop this, I will firstly consider the conditions. It was published in the Bulletin of Calcutta Mathematical Society. And Kramer in 1947. Okay, so the name has stuck as Rao-Kramer or Kramer-Rao inequality. We first state some regularity conditions. So by conditions, regularity conditions, we mean that the probability distribution satisfies certain conditions. Under those conditions, this inequality will be true. Okay, so these are known as Wolfowitz regularity conditions. Okay. I am giving the most updated form. So let us consider, say, x1, x2, xn be a random sample from a distribution having probability mass function or probability density function. Now let me give some notation, say fx theta. So in the beginning, I am writing it for one parameter only, okay, theta. an estimator delta x is considered for theta. So in general, we can consider estimation of theta, theta square, theta log theta, or any function of theta. So initially I am writing for the inequality for theta, and then we will see that you can just modify it by a certain coefficient, and then you can write for g theta also. So that is not a difficult thing. Theta belongs to some set, say I, where I is an open interval on the real line. So I have been using parameter space, okay, as script theta. So I am just writing here theta to denote an interval, but obviously we can use this notation also, okay. Then the second condition is the partial derivative of the PDF or PMF exists for all theta, okay. Let me just say this again actually. Like I mentioned that the parameter space is an open interval. You consider the exercises that we have done. For example, you consider binomial distribution in which we take n and p as the parameter. So if I take n, then n is actually taking only positive integers. So for n, this inequality will not be true. The inequality will be derived only for p because we take p to be lying between 0 and 1. Similarly, if you consider say geometric distribution, there is again parameter p which lies in the interval 0 to 1. If you consider say normal distribution, then normal distribution mu lies between minus infinity to infinity. Sigma is positive. So they are all on the intervals. So this result is valid where we are talking about the space to be of intervals. Why? Because I am going to talk about the derivatives, etc. So derivatives, as you know, we cannot define in the discrete range because we are taking limit, like we write f of x plus h minus f of x divided by h as limit h tends to 0. So if you don't take interval, then this will not be valid, okay? But fortunately, in statistics, whatever distributions we consider usually, there the parameters are in the interval. So then we consider another condition, that is the say delta x. So delta is some estimator, as I mentioned just here, that delta is an estimator here, okay. So for that estimator, we should be able to write down this joint expectation then you may ask the question that whether this should be integral only or this can be anything else. So if it is a density function, then it is an integral. If it is a probability mass function, then this will be summation, okay? That means this is like this. And this sum is over x1, x2, xn, okay? This can be differentiated under the integral or summation sign.
Sir?
Yeah.
Can you repeat what we will do in the second case for discrete distributions?
In the discrete case, this will become summation. No, basically, what I have written here, this is what is this term? This is nothing but expectation of delta x. Okay, this is nothing but the expectation. So expectation is integral if you have a continuous distribution, and if it will be summation if it is a discrete distribution. Okay, is that okay?
For the partial differentiation, sir.
This
In the
term,
condition 2.
this is a function of theta alone because x are integrated here, xi's are integrated. So this is a function of theta. So I am saying this is this can be differentiated under the integral or summation sign with respect to theta. Because this is a function of theta only, x will go away because you are integrating or summing with respect to that.
Sir, I was asking about the condition 2, where you said the partial differentiation.
Yes. So what is the problem here?
Yes, sir. What will we do for discrete case? Since there will be, can we differentiate them?
This is differentiation with respect to theta, so that we can do. Because theta lies in an interval. Theta lies in an interval. See, whether you are taking geometric distribution or Poisson distribution. See, what is Poisson? E to the power minus lambda, lambda to the power x by x factorial. You can differentiate with respect to lambda because lambda is on an interval, isn't it?
Yes, sir. Okay, sir.
So this differentiation, etc., is with respect to theta. Okay. So I don't know, any of you have done the real analysis course? No.
No, sir.
Okay, so I will not use, otherwise I can actually plug in something which I can use only single notation. I have to write otherwise dx and this sigma separately. Otherwise I can just plug in here mu here, then discrete and continuous both cases are taken care of. But since you are only in second year student, so you have not done the measure here. Otherwise I can just use the Lebesgue-Stieltjes integral in place of the ordinary integral. So then it takes care of all the cases. Anyway, so because I have to look at the level at which you are studying. Right now you are only in the second year, so you have not done the those Lebesgue-Stieltjes or Lebesgue integrals. So let me just move ahead. So next one is this expectation of del by del theta log of fx theta. This is positive for all theta. Okay. So now I state the inequality here. Then the variance of delta is greater than or equal to 1 plus b prime theta whole square divided by n times expectation of delta by delta theta log of fx theta whole square. So this is the inequality. Okay, that means variance of an estimator delta is always greater than or equal to this quantity. In particular, if b theta is 0, then delta x is unbiased. Then b prime theta will be 0. Then it becomes variance of delta is greater than or equal to 1 by n times expectation del by del theta log fx theta square. Note here the right hand side does not involve delta here. So what we are saying, the variance of an estimator is always greater than or equal to certain quantity. So if the variance becomes equal to this quantity, suppose I am taking for b theta is equal to 0, then it becomes minimum variance unbiased estimator. This problem I mentioned to you when I was defining the UMVUE. I gave certain necessary and sufficient condition and certain characterization, but that does not lead you to an UMVUE. So in order to prove that an estimator is UMVUE, you need some methodology. So this is one of the earliest methods which was developed. Later on, I will show you some other method also, which is much more efficient method. But anyway, let me start with this. So proof with your modern tools that you are having, the proof is quite simple. So I will write the, because expectation is there, so I will actually use only either integral or summation, because both are possible. So let me just consider this here. So this is delta x product of fxi theta I is equal to 1 to n dx. So dx1, dx2, dxn, I'm just writing as dx just for the sake of brevity. Okay. If you are having any doubt in the notations, please ask immediately. Okay. So this is a n-fold integral, but I have written a single integral only because dx1, dx2, dxn, I am just writing as dx only. Okay. Now this term I will differentiate under the integral sign. Okay. See, delta x does not have any theta, so when you differentiate, you have to actually differentiate this product term here. So how do you differentiate the product term? There are two methodologies. One is you take log here. So when you take log here, then each term will be separately differentiated. That will give me 1 by fxi theta into del f by del theta. Okay. And then when you remove the log, then it will be multiplied here again. So this will give you straightforwardly the following term, that is summation del by del theta log of fxi theta I is equal to 1 to n multiplied by the product of this. And that is equal to 1 plus b prime theta. So are you satisfied with this term? This differentiation, are you clear?
Yes, sir.
You can look at it in a different way also, because this is a product of n terms. So you take one of the terms. So for example, if I consider fx1 theta, so if you differentiate that, you will get del f by del x1, del f by del theta of this x1 thing. Now you consider, you divide it by the same term and multiply. So the product remains intact here, and you will get del by del theta log of fxi theta. Now I will use some notation here. Let us put, see this particular term, I will call sx theta. Okay. So that is sigma del by del theta log of fxi theta. Okay. So this becomes then.
Sir, can you tell why that log term comes?
So you have the derivative here of this particular thing. Okay. So for example, if I consider derivative of fx1 theta, what I will get here, this I need not put here. Yeah. I will get del f by del theta, isn't it? Del f x1 theta by del theta. So that term is missing now from the product, because product has all the terms. So in order to make the product intact, I will multiply and divide by fx1 theta. So now I have got the term like del f x1 theta by del theta divided by f x1 theta, which is nothing but del log f of x1 theta by del theta. Is that okay?
Yes, sir.
So now it has become product of two terms. this is nothing but expectation of delta x into Sx theta, that is equal to 1 plus b prime theta. That is what we have got now. Let me call this relationship now 2. Okay. This Sx theta, I am calling this particular term. Let us further analyze this. If I am considering integral of the densities, then it will give me 1. Okay. Once again, what I can do, I can differentiate this. So earlier this Sx theta was coming by, but now that term is not there. Only this much is there. So this is giving you again sigma del by right hand side will become 0. But this is nothing but again Sx theta. So this is giving you expectation of Sx theta is 0. Now, if you consider covariance between delta x and Sx theta, this is equal to expectation of delta x into Sx theta because covariance of xy is expectation of x into y minus expectation x into expectation of y. Since expectation of Sx theta is 0, therefore it is reducing to this much only. And expectation of delta x Sx theta, just now we have written, it is equal to 1 plus b prime theta. Okay. This is what we have written, expectation of delta x Sx theta is 1 plus b prime theta. So we have got this is equal to 1 plus b prime theta. Once again, I will make use of the correlation inequality or covariance inequality. So we have 1 plus b prime theta square. I can write it as covariance square delta x Sx theta. Covariance is less than or equal to variance of delta x into variance of Sx theta. Okay. This covariance correlation inequality I have told you earlier that rho lies between -1 to 1. So rho square is less than or equal to 1. So covariance square is less than or equal to variance product. Now again, so variance term has come here and this term has come here. Let us look at what is variance of Sx theta. Okay. So variance of Sx theta term also let us try to figure out what it is. That is equal to variance of sigma del by del theta log of fxi theta. Now these are x1, x2, xn are independent and identically distributed random variables because x1, x2, xn is taken as a random sample. And this term which I have written here, del by del theta log of fxi theta, which is a function of xi alone. So these terms remain independent. So this becomes sum of the variances and each of them is from the same distribution. So I can just replace it by n times variance of del by del theta log of fxi theta. See, if I write integral of fx theta dx is equal to 1 and differentiate, what I will get del f by del theta into dx, that is equal to 0. So I can write it as del fx theta by del theta by fx theta into fx theta dx is equal to 0, which is nothing but expectation of del log fx theta by del theta is equal to 0. So variance of this becomes nothing but, so I can remove this I from here, okay, because it is the same for all of them. So I can just write x here, okay. So this becomes expectation of del by del theta log of fx theta whole square, because expectation of del by del theta log fx theta is 0. So variance of x becomes expectation of x square. This quantity I will give you a name here. Okay, this is called Fisher's information in X. Okay, Fisher's information measure. So if you substitute it here, what you have got in the 4, this variance of Sx theta has become Ix theta. So from 4 we get variance of delta is greater than or equal to 1 plus b prime theta whole square divided by Ix theta. So this is the Rao-Kramer inequality. This concept of information, actually later on it is given in 1947 by Claude Shannon in the communication channels, and now information theory is a well-developed subject in for all the engineers and scientists. But the first such measure was actually given by Fisher in statistics, and this is called Fisher's information measure. So in X, we have to say this is about theta. Okay. So what is the purpose of sampling? The purpose of the sampling is to derive certain inference on the parameter of the population. So that means sample gives you some information. So how to measure that information? See, estimation is one thing, testing of hypothesis is another thing, confidence interval is another thing. But roughly speaking, how much information about the parameter is available in the sample? So for that, this measure was developed by Fisher in 1920s basically. But it turned out that actually it reflects the information. So we will talk about that a little later when I talk about another concept, that is the sufficiency based on this. But right now it is used here in the variance of the unbiased estimator itself. So, so in particular, if delta x is unbiased for theta, then b prime theta is 0, and so Rao-Kramer inequality that variance of delta is greater than or equal to 1 by I x theta for all theta. Okay, where delta is, okay, that we have already written that it is unbiased estimator. Okay, is the proof clear to all of you? Do you have any doubt here? Is it clear to all of you?
Yes, sir.
First of all, let us analyze this one. So I have given it as an inequality. I mentioned to you that if variance of delta x is equal to 1 by I x theta, then this will become minimum variance unbiased estimator. But the question is that when it will happen. Okay, so let us analyze that. Condition for attaining the lower bound. Okay, so how the inequality has been attained? It is attained by using the covariance or correlation inequality. Now in the correlation inequality, you know that the equality is achieved if x and y are linearly correlated with probability 1. So the same condition will be true here, because what we are using here, we are using for the covariance between delta x and sx theta, and I am writing it is less than or equal to variance of this. So covariance between delta x and sx theta is equal to this one, that is square root of this, provided delta x and sx theta are linearly related with probability 1. So that is basically the condition for that. So let me write it here. The equality in if and only if delta x and sx theta are linearly related with probability 1. That is, there exists functions, some functions. So let me give some name here. Say, suppose I say alpha theta, beta theta, such that delta x plus alpha theta sx theta is equal to beta theta with probability 1. So let us look at the applications here and see that in which problems we will be able to get UMB UE. Okay. So let me start with, say, let x follows binomial NP. Okay, and I take n is known here. So P is the parameter. Okay, So we want to find Rao-Kramer lower bound. So here P I am taking. So for P, I want to find out what is the lower bound. Okay. So let us write down the probability mass function here. NCX P to the power x 1 minus P to the power n minus x. So what I need to calculate? Ix theta. So Ix, what is the definition? We have written it is actually expectation of del log fx theta by del theta whole square. Okay, this term here, because n is 1 here, one sample I am taking. So let me consider here log of fxp. You will see that in many of the statistical methodologies that I will be teaching you, the calculations are of similar nature. For example, this log of f I have done for the maximum likelihood estimation also. So therefore, if you are seriously doing the course and you are doing the evaluations, then you will find the things are very comfortable, because the properties that you prove for one of them can be utilized for others. So this is x by p minus n minus x by 1 minus p. Exactly this term we have calculated as the log likelihood function, and then differentiation we had done. So exactly this term had come here. So this is nothing but x minus np divided by p into 1 minus p. If you remember, I had looked at the sign of this increasing and decreasing, and then we had found out the maximum likelihood estimator. So exactly that term has come here. So now, what is the lower bound? So for the lower bound, I will calculate the information here. That is expectation of del log fxp by del p whole square. So that is nothing but expectation of x minus np by p into 1 minus p whole square. So this is nothing but 1 by p square into 1 minus p square variance of x, because expectation of x minus np square is nothing but variance of x, that is np into 1 minus p. For binomial distribution, you remember the moments. So this is becoming nothing but n divided by p into 1 minus p. So I'll write Rao-Kramer as RC lower bound for variance of an unbiased estimator of P as 1 by IXP. So that becomes P into 1 minus P by N. Is this calculation clear to you? Is this calculation clear? Now the objective is not just to evaluate this. The objective is actually to find out the UMVUE. Now you remember, if I consider T is equal to X by N, then this is unbiased. So what is variance of T? That is variance of X divided by N square. That is N into P into 1 minus P by N square. That is exactly this term, the RCLB. So we have proved that T is equal to x by n is UMVUE for P. You can actually guess it here. See, we have obtained this SXP here. This is actually SXP because only one observation is there. So this is SXP. I can write it here, SXP. So SXP, if you see, this is a linear function of x. So delta x, if I am taking x by n, then x by n and SXP, they are linearly related with probability 1. So from here also you can conclude that any linear function of x will be UMVUE of its expectation. So for any AB where A is of course non-zero, this AX plus B will be UMVUE for A and P plus B. So you are actually able to prove much more. Also, you can prove that suppose I am asking for P square, we have obtained the unbiased estimator as x into x minus 1 by n into n minus 1. But from here now you can say that it will not be UMVUE. Although it is a good estimator, it is unbiased, but it will not be UMVUE because the variance that we are having, the linearity, it is linear with x. So it will not be linear with x into x minus 1. Also shows that variances of non-linear functions of x will not attain the lower bounds for their expectations. Okay. I am putting a comment here, though they may still be UMVUEs. But for that, we have to use some other method for proving that they are UMVUE. Okay. Let me move to other applications. I mean, apart from binomial, let us take say other distribution. So let us consider say x1, x2, xn following Poisson lambda. Okay. We want to find RCLB for lambda. Okay. So for the variance of an unbiased estimator of lambda, what is the Rao-Kramer lower bound? We want to calculate that thing. Okay. So fx lambda, that is equal to e to the power minus lambda, lambda to the power x by x factorial. Once again, you will see that the nature of calculation is similar to the one which we applied for the maximum likelihood estimation. So del log fx lambda by del lambda, that is equal to -1 plus x by lambda. That is nothing but x minus lambda by lambda. So expectation of del log fx lambda by del lambda whole square, that is equal to expectation of x minus lambda by lambda whole square. That is 1 by lambda square variance of x, because expectation of x is equal to lambda. So expectation of x minus lambda square becomes variance of x. In Poisson distribution, you remember the variance is also lambda, so it is 1 by lambda. So ix lambda, that is n times this, so it becomes n by lambda. So the lower bound for the variance of an unbiased estimator of lambda, that becomes 1 by this, so that will become lambda by n. So is the calculation clear to you?
Yes.
So you remember the estimators for the Poisson case. I had considered x bar, s square, and so on. So if I consider x bar, so let me write here. T1 was x bar. So expectation of T1 was lambda. What is variance of T1? That is lambda by n, which is equal to this quantity. So T1 is equal to x bar is minimum variance unbiased estimator for. So actually this is the method by which we are able to prove that the certain estimators are minimum variance unbiased estimators. Otherwise, we can just calculate several unbiased estimators and we are not able to show that whether which one of them will be actually UMBUE, because then you have to compare all of them. But comparing all of them becomes impossible, because in case there is more than one unbiased estimator, then how to find out? Okay. Again, this part you could have guessed from here also, because this is a linear function of x. If I am considering Sx lambda, see here I have written for one term, but if I write for full sample, so if I consider Sx lambda, what it will become? It will become sigma I is equal to 1 to n xi minus lambda by lambda. That is basically n times x bar minus lambda by lambda. So this is a linear function of x bar. So Sx lambda and x bar are linearly related. Linearly related with probability. So a x bar plus b will be UMBUE of a lambda plus b for all a and b. Okay. However, since I am getting x bar and linear functions of that, so if I am taking non-linear functions, then using this method I cannot prove that what is UMBUE for lambda square, what is UMBUE for lambda cube, or any other thing. However, for the direct parameter I am able to get it here. Is it okay?
Yes, sir.
So this methodology that I have given, it is for one parameter. If I have several parameters, then I have to write a multi-dimensional thing, because then derivative will not be one, because partial derivatives, then you will get a vector as well as a matrix, because if I am considering this del by del del f by del theta whole square, so I will show you another. Let me just write it as a lemma here, because the relationship also, because we can generally use in statistics various equivalent terms. So what is the equivalent term for here? Let me just mention it here. So whatever regularity conditions are given, expectation of del by del theta log of fx theta whole square. This was the term which I am considering in the information matrix. Basically, n times of this is information measure. This is equivalently if I take second derivative, but then I have to put the so this is an alternative expression for this. I can actually write down a small proof for this. Let us just consider this here, okay? So if I consider del 2 log of fx theta by del theta 2, that is equal to del by del theta of del by del theta log of fx theta, and that is nothing but del by del theta fx theta divided by fx theta. Okay. So if I consider the derivative here of a ratio, I can express it like this. Del 2 fx theta by del theta 2 into fx theta minus del by del theta fx theta, and then second this one, so it will become square of this, and whole thing divided by f square x theta. So if I take expectation on both the sides, expectation of del 2 by del theta 2 log of fx theta, that becomes equal to, the first term will give me f double prime x theta into fx theta and divided by f square x theta into fx theta dx. So this term gets cancelled out, minus f prime x theta by fx theta square fx theta dx. So this term is nothing but 0, because it is nothing but the derivative of the integral fx theta dx, because that is equal to 1. So if you differentiate once, you get 0. If you differentiate twice, then also you get 0. Here actually this f double prime I have written, it is simply derivative with respect to theta, because I am not differentiating with respect to x anywhere. So just I have written for abbreviation, otherwise the term becomes little lengthy. So this is nothing but minus expectation of del log fx theta by del theta whole square. So proof is of course very simple, just I wanted to show. So many times actually when we want to generalize this lower bound to higher dimensions, then we will use second order derivative. Okay, is this proof clear to all of you?
Yes, sir.
Okay, so I'll just maybe write one exercise. I think you can also try one on your own. Okay, so let
Sir, is
me.
the double integration of double derivative is 0 only because since the integration.
Okay, just I will write here. That is simple because if you consider this is 1, if you differentiate with respect to theta,
Yes, sir.
what you will
Yes,
get
sir.
del by del theta fx theta dx is 0. If you differentiate again, that is also 0. Okay, is that okay?
Yes, sir.
Okay, let me just write some exercise because you can try yourself something. So let me write say exponential distribution 1 by theta e to the power minus x by theta. Okay. Find RCLB for theta and find UMVUE. And let me write another exercise x1, x2, xn from normal 0 sigma square. So I have changed the parameter here. Find RCLB for sigma square and find UMVUE. And let me put x1, x2, xn following normal mu1. Then find RCLB for mu and find UMVU. So exponential distribution and normal distribution, I have given two forms. In one form, I am taking variance term. In another form, I am taking the mean term. Because I have developed the RCLB for one parameter only. So I am not taking normal mu sigma square. Okay. Are the problems clear to all of you? So I'll give a break for maybe 5 to maybe 10 minutes. Okay, I'll give a break for 10 minutes. You please attempt these problems and tell me the solution. Okay, I'll give a break for 10 minutes here. Okay, so let me ask, have you obtained the lower bounds for these problems? Let me ask the exponential first one. So let me ask one of you. Yeah, Vishal.
Yes, sir. Doing so.
Priyanshi, have you done it?
Sir, may I?
Yeah, please tell.
The theta square by n.
Okay, so in the first case, it is theta square by n. For exponential distribution, this x1, x2, xn following 1 by theta e to the power minus x by theta. So RCLB for theta, that turns out to be theta square by n. So what is UMVUE then? What is UMVUE? If the RCLB is obtained, then which estimator will achieve that? Jay Kumar?
Sir, I am trying, sir.
Okay.
Sir, x bar.
X bar. So if I consider T to be X bar, then variance of X bar is theta square by n. Because in the exponential distribution, you know that the variance is lambda is 1 by lambda square. So here 1 by lambda is theta, so it becomes theta square. So for X bar, it will become theta square by n. So that is equal to RCLB. So X bar is UMVUE for theta. Also, if you look at the Sx theta term, what is Sx theta here? That is x minus theta by theta square. So if I consider summation here, then it is nothing but n x bar minus theta by theta square. So this is linear function of x bar. So any since x bar and Sx theta, they are linearly related with probability 1.
Sir, I have a small doubt.
Yeah.
How do you say that they're linearly related, but how to say that with probability 1? I can't understand, sir.
Because this is for random variable, no? This is for random variable.
Yes,
so
sir.
what is the meaning of the two random variables? Suppose I say a random variable x is equal to random variable y. What is the meaning of this? How can I write like this?
Sir, because
They are realizations of a sample space, isn't it? Because they are not one value. X is not one
Yes.
value. It
Yes.
is x is a function from omega to r. Similarly, y is a function from omega to r, isn't it? So what is the meaning of x is equal to y? That means x omega is equal to y omega for all omega, isn't it?
Yes, sir.
This is pointwise equivalence. But in the case of random variable, we need not have pointwise equivalence. It is enough if we consider probability of the set this to be equal to 1. That is enough for us. Pointwise equivalence is not required because that is much more stringent. This is enough. Okay. So here what we are able to obtain, because the value itself is here x bar something, some linear function. So that means the two are equal. Okay. So therefore, I can easily make the statement that they are linearly related with probability 1.
Yes, okay, sir.
Okay, let us look at the second problem for the estimation of the variance. For the estimation of the variance, have you obtained the lower bound?
2 sigma power 4 by n.
So if I am considering this problem x1, x2, xn following normal 0 sigma square, then RCLB is equal to 2 sigma to the power 4 by n. So what is UMVUE? Can you obtain from here? So what is an estimator which will be UMVUE here?
N minus 1 by n.
N minus 1 by n. What? N
S
minus
square.
S square. What is the variance of that?
Two sigma power 4 by n.
Have you checked that? Can you check that? I'll just give you a hint here. Actually, you have written the fx here. You have written that 1 by root 2 pi sigma square e to the power minus x square by 2 sigma square. Okay. So log of fx, that is equal to minus 1 by 2 log 2 pi minus 1 by 2 log sigma square minus x square by 2 sigma square. So if I consider del log f by del sigma square, that is minus 1 by 2 sigma square plus x square by 2 sigma to the power 4. So that is equal to x square minus sigma square divided by 2 sigma to the power 4. So if I write down Sx sigma square, that is sigma of xi square minus sigma square. So I can put n sigma square there. Yeah. Minus n sigma square divided by 2 sigma to the power 4. So you can easily see that it is a linear function of sigma xi square. So if I consider t is equal to sigma xi square by n, expectation of this is nothing but n sigma square by n, that is equal to sigma square. So, and of course, I mean, variance of this is nothing but 2 sigma to the power 4 by n. So that is RCLB. But you don't have to actually evaluate it. From here itself, you can say that T is UMVUE. I hope these calculations are clear. Actually, you should look at this. This term is sufficient to tell you or to guess that what would be the UMVUE. You don't have to actually worry too much about any other estimator. Just look at the form of Sx, and from Sx you can actually make a guess. So linear functions of sigma xi squares will be UMVUEs of their expectations. So since in this case I have to look at for sigma square, so I just divide by n here because expectation of x square is sigma square here. So that gives you the UMVUE. I hope the problem is clear to all of you.
So since we assume that since the theorem says if the variance is the least lower bound, then it is linearly dependent. So we guess that from the function.
Right. Yeah, this actually, apart from giving a lower bound, it also gives you a hint that how to actually search for the UMVUE. Okay, but of course it has a limitation because only linear functions of sigma xi squares will be UMVUE from this methodology. But of course you may have other problems, no? Like you may like to estimate say sigma to the power 4, or because that appears, for example, in the measure of kurtosis. You may like to, so similarly in other problems, certain other parametric functions may be of interest, but then this method will not give you the UMVUEs for that, because in this one the strict condition for attaining the lower bound is given there. Now it may happen that in a given problem, none of the estimators has the lower bound, the variance equal to the lower bound. So then how do you get the minimum variance unbiased estimator? So I will talk about those methods later on. But at least in the standard problems, you are able to get the result here. So I gave you the next problem, that normal mu1. For this one, what is the answer?
Sir, 1 by n.
1 by n. Oh, RC lower bound. Okay, that is equal to 1 by n. What is the MVUE here? Again, if you use the same methodology, what you will get?
X bar.
X bar. So variance of X bar is 1 by n. So X bar is UMVUE here. Note here that in this normal distribution, actually there are two parameters, mu and sigma square. But I have not taken simultaneously both the parameters. In one case, I took sigma square is equal to 1. That means mu is the parameter. In the second case, I have taken normal 0 sigma square. So mu I have taken to be 0, sigma square is the parameter. So from the Rao-Kramer lower bound methodology, I am able to obtain in separately for both of them. But I cannot apply jointly this method here. And actually that is a limitation of this method. So I will tell you after some time that how to obtain the minimum variance unbiased estimators in those cases. So there is some other method also. Right now we are discussing only this one. Okay. So I hope these examples are clear to all of you.
Yes,
Yes,
sir.
sir.
Okay, so let me take some other examples where I will show you that the bounds are not attained. Okay. So let me take another example. So for example purpose, I am taking a single observation. So fx theta is equal to theta into 1 minus theta to the power x, where x can take values 0, 1, 2, and so on. And of course, theta is actually it is written in terms of p in the geometric, but I am just using theta because for the derivation purpose, I have used theta, which looks little bit more convenient. All of you have seen this distribution, this geometric distribution in your probability course.
Yes.
Only thing is that some of you might have studied from x is equal to 1, 2, and so on. In that case, this becomes x minus 1 here. So it hardly matters because it is the method of representation. See, if I am considering the number of trials needed before the first success or up to the first success. So depending upon that, it will start either from 0 or from 1. Okay. So both the representations are there. So if I consider here the derivative, that is 1 by theta minus x by 1 minus theta. Okay. Okay, so you have to use the moments of the geometric distribution. I hope all of you remember some of those calculations, or if you don't remember, then just revise that. Just see what is the expectation of x, what is the expectation of x square, etc. So this will become expectation of x by 1 minus theta by 1 by theta whole square, because here the mean was 1 minus theta by theta. Okay, so if you start from 1, then it is 1 by theta, and if you start from 0, then it is 1 minus theta by theta. So it is the variance of this divided by this square. So it gives you this term. So I have taken n is equal to 1, so I will write only theta square into 1 minus theta. I am not writing theta square into 1 minus theta by n here. But the problem here is actually Sx theta is linearly related to x. Okay, x is coming here. But expectation x is not theta. Expectation x is 1 minus theta by theta. So the lower bound for estimation of 1 by theta is attained, for the estimation of 1 minus theta by theta is attained, but for theta it will not be attained. Of course, you may ask the question that why should I worry about theta? If I can obtain the UMUE for the mean is 1 minus theta by theta, that should be enough. But actually what happens that the statistical inference is not based on the only mean and variance. Statistical inference may be for any parametric function, because many parametric functions are of interest here. So since expectation of x is 1 minus theta by theta, the RCLB for 1 minus theta by theta is attained. However, for theta, it is not attained. I will show you actually one unbiased estimator. What is the interpretation of theta here? It is the probability, we can say, suppose I take probability of 0. Okay, so probability of 0 is actually theta here. So if I consider an estimator as I write it as equal to 1 if x is equal to 0, and it is equal to 0 if x is greater than 0. That means it is equal to 1, 2, and so on. Then what will be expectation of Tx? That is 1 into probability of x equal to 0 plus 0 into probability x greater than 0. So that is equal to theta. Then Tx is unbiased for theta. Let us look at what is variance of this one. So expectation of t square is also the same, because it is 1 square into probability x equal to 0 plus 0 square into probability x greater than 0. So that is again theta. So variance of Tx becomes theta minus theta square, that is theta into 1 minus theta. But this is obviously greater than theta square into 1 minus theta, which was the RCLB. So Tx does not attain RCLB. Later on, using another method, I will show you that actually it is UMVUE. Okay. So let us take an unbiased estimator and I will give some name here. Let us call it say delta x. Okay. So what is the condition that I should write? Expectation of delta x is equal to theta. Okay. Now this condition you write down properly. This is a discrete distribution, so expectation means sum multiplied by the probability mass function for x is equal to 0 to infinity, that is equal to theta. So you write down the terms corresponding to x is equal to 0. This is delta 0 into theta, then delta 1 theta into 1 minus theta plus delta 2 theta into 1 minus theta square and so on. That is equal to theta for all 0 less than theta less than 1. Let us look at the solution of this here. If we equate the terms on both the sides, so I will write, see, you can divide by theta on both the sides. So what I will get, delta 0 plus delta 1 into 1 minus theta plus delta 2 1 minus theta square and so on. That is equal to 1 for all. The left hand side is a power series in powers of 1 minus theta. Okay. And it can equate to right hand side for all theta if and only if all coefficients match. Okay. So I will get delta 0 is equal to 1, delta 1 is equal to 0, delta 2 is equal to 0 and so on. That means delta x is equal to Tx for all x. So you get only one unbiased estimator. So Tx is UMVUE. Is the proof clear? Is the proof clear?
Yes, sir.
Now in place of estimating theta, suppose I am considering g theta. Okay. So actually the first proof or the first statement that I have given, actually I have given for theta plus b theta. So what did I get there? The lower bound was 1 plus b prime theta whole square by ix theta. So if I consider estimation of g theta, I can write g theta as equal to theta plus b theta. Okay. So in the numerator, I will get g prime theta whole square. So the lower bound will be simply modified. So the condition for attaining So since basically what is happening is that any estimator which attains the lower bound, it is actually a linear function of Sx theta. If that is so, then you can actually characterize all functions which are actually for which the linear lower bound is attained. So I can state it in the form of the following theorem. Then the class of parametric functions so if for g theta the RCLB is attained, then for all the parametric functions for whom this RCLB is attained, they will be simply linear functions of g theta. So proof is of course based on this characterization of equality itself. So let Tx be an unbiased estimator of g theta and let variance of T be equal to RCLB for g theta. Then Tx and Sx theta, they are linearly related with probability 1. That is, there exist functions alpha theta and beta theta such that Tx plus alpha theta Sx theta is equal to beta theta with probability 1 for all theta. Now what we do, we take expectation on both the sides. So expectation of Tx plus alpha theta, expectation of Sx theta is equal to beta theta. So this means g theta and expectation of this is 0. So that means this is beta theta. Now let us consider h theta is any other parametric function for which the lower bound is attained. Okay. Now let h theta be any other parametric function for which there is an unbiased estimator, say ux, such that variance of ux is equal to then again we have the same statement that ux and sx theta are linearly related with probability 1. That is, there exist, say, alpha star theta, beta star theta, such that ux plus alpha star theta sx theta is equal to beta star theta for all with probability 1 for all theta. So once again you take expectation. Left hand side will give me h theta plus this is 0. So this is equal to beta star theta. So now let us write down the two statements. Tx plus alpha theta sx theta is equal to g theta with probability 1 for all theta and ux plus alpha star theta sx theta is equal to h theta with probability 1 for all theta. So for fixed theta, let us eliminate sx theta. Okay. So suppose I say for a fixed theta is equal to theta naught, some fixed value I am taking. If we eliminate, that means I will multiply this by alpha star theta naught tx minus alpha theta naught ux, that is equal to alpha star theta naught g theta naught minus alpha theta naught h theta naught. Okay. With probability 1. So you take, so these are some fixed numbers. We can say some a times tx plus b times ux is equal to some c, because these are all fixed values. So now if you take expectation, a times g theta plus b times h theta is equal to c. So this gives that g theta and h theta are linearly related. So basically this sums up this entire inequality here, that for all the parametric functions for which we have to attain, they should be simply linear functions of the term which is appearing in Sx theta. Basically that answers all those questions. Okay, is this discussion clear to all of you?
Yes, sir.
Now I define exponential family of distributions. So a random variable x is said to have distribution belonging to an exponential family. Note here that I am not calling it as exponential distribution. This is exponential family. Okay, so this is a bigger terminology. If it has PMF or PDF of the form C theta hx e to the power q theta tx. So if the distribution can be written in this particular form, that means a function of theta multiplied by a function of variable, then e to the power some term which is again a product of a function of parameter and a function of variable. So this is called a distribution in exponential family. Okay. Okay, why these are important? So actually, again, these were introduced in 1930s by R.A. Fisher, because he observed that some of the standard distributions that are there, they actually belong to this. So let me actually show you that the standard distributions that we consider, they are actually in this. So let us consider, say, binomial distribution. Okay. So I consider X follows binomial NP, where N is known. Then how do you write down the form of the probability mass function? It is NCX P to the power X 1 minus P to the power N minus X. X is equal to 0, 1, 2, N, and P is between 0 and 1. See, sometimes we put 0 less than or equal to P less than or equal to 1, sometimes, and inequality is there, sometimes equality is also there. Okay, so I am writing like this. This term we can write as NCX 1 minus P to the power N, P by 1 minus P to the power X. And then you can further write it like this. So 1 minus P to the power N, NCX e to the power X log P by 1 minus P. So this is of the form that I wrote. This is now C of P. This is Hx. This is your Tx, and this is Q of P. Okay. So this is, so for N known, the binomial distribution belongs to exponential family. If n is not known, then I will not be able to write like this, because then n will come there, this ncx term is there. So I will not be able to write in that particular fashion. But if n is known, then just with p I am able to write it as a exponential distribution, exponential family of distribution. Let us take another example here. So I am taking, say, Poisson distribution. Okay. What is the probability mass function of Poisson distribution? You can write it like this: e to the power minus lambda 1 by x factorial e to the power x log lambda. So if you compare with the form of the exponential family, then this is nothing but your c of lambda, this is hx, this is tx, and this is q of lambda. So the Poisson distribution also belongs to exponential family. Maybe I will stop at this point here. It's almost time today. So I will actually, because exponential family, you will see that a lot of nice things happen with the exponential family of distributions. Because ultimately what is happening is that whatever we do in statistical inference, we will work with the probability density function or the probability mass function. So if the probability density function or mass function satisfies some nice properties, then actually for those distributions, those nice results will come. So that is what we will observe. And later on, actually, this is the major cause, or you can say major reason, that why statistical methods are so popular in sciences, engineering, social sciences, because statistical inference procedures are satisfying certain generic properties. And in many of the real world applications, the form of the model that you get, that falls into certain standard category, and therefore the results which are developed for them can be applied. And that is why the use of statistical methods is very much prevalent all through. Like for example, you might have noted, like now COVID situation is there. So for COVID itself, every day you will find some new model is given, some statistical model, when the peak will come, how much mortality will be there, and so on. So many kind of predictions are done using statistical methods. So anything is there actually, like whether for economic recovery, for growth rate, for agricultural production, for anything, statistical methods are used. And the reason is that the standard statistical models, they satisfy certain very, very nice properties. So a person who is a statistician, actually he just tries to see that the given data or the given problem, which model it is applicable there, and then he is able to apply that. I think with this I will stop today's class at this point. Do you have any question at this point? Okay, if there is no question, then I will stop.
Thank you.